So now that we've discussed orbitals, let's talk about how we use orbitals to describe electrons. So remember that orbitals are just probabilities of finding electrons, okay? So there are two ways that we're going to do this. One of them is orbital notation, and the other one is electron configurations, okay? In orbital notation, an unoccupied orbital would be represented by a line, okay? Something that looks like that. Each electron is represented by an arrow, and the arrows could be either an up arrow or a down arrow, and we're going to talk about the difference between those in a second. An orbital containing one electron would thus be the orbital with one arrow. And the convention is when you put one electron in that the arrow points up, okay? Lines are then labeled with the shell and subshell letter. Okay, so to make a proper electron configuration, one must determine the energy levels and add electrons one by one according to the rules, which we're going to go over. So rules for adding electrons. One is the Aufbau principle. An electron occupies the lowest energy orbital that can receive it. All right, now what do I mean by that? Well, the lowest energy orbital possible is this 1s. So we always start with the 1s, okay? So, oops. For example, if I do hydrogen, all right, I'm gonna say that hydrogen has one electron, okay? I can go look at the periodic table to prove that to you. Okay, hydrogen has one electron. So sometimes it's helpful to remember that. That's one electron. Okay, and so the one electron is going to go in the lowest energy orbital that can receive it. Well, the lowest energy orbital is the 1s. So here's my line representing that orbital. I'm going to label it the shell and the subshell. That's the 1s. And then I'm going to put one electron in there. Okay, now this is kind of like this electron's address. It's like a 1s, okay? Now the problem is two electrons cannot be exactly the same. So for example, with helium, now let's take a look at helium. Helium has two electrons, all right? So here's two electrons. And I know that each orbital can hold two electrons, okay? Each orbital can hold two electrons. So there is room in the 1s orbital for each of these electrons. But if I do it like this, then these electrons are both the same, okay? So the up and down arrows actually represent something called spin. And electrons spin about an axis a lot like the Earth does, okay? And they could spin clockwise, or they could spin counterclockwise. And the way that we get around this two electrons cannot be exactly the same is we don't do this, but instead we do one spinning one way, let's say the up way or clockwise, and one spinning the other way, counterclockwise, okay? Now these electrons aren't exactly the same. They're spinning different directions. Okay, so how about beryllium? All right, well, beryllium has 4 electrons. Ooh, I skipped ahead. Okay, so 4 electrons. So I'm going to use Aufbau principle. So I'm going to put 2 electrons in the 1s, one going up and one going down to make sure that they're not the same. But now I've got to do something. I've only used 2 electrons. I've got 4 total. I need to go to the next highest energy level orbital. Okay, oops. So the next highest energy level orbital is going to be, I'm going to go from the 1s to the 2s. So I'm going to go up to here, okay? So, oops. Let's scroll this down. Move this over. So I'm going to go from the 1s to the 2s. And the 2s, remember, is an s, subshell, which means it only has one orbital. Okay? And I'm going to put 2 electrons into that orbital. So it's this 1s with 2 arrows and the 2s with 2 arrows. Okay, well, what about boron? Now boron has 5 electrons. Okay, so you can see that I'm going to need to kind of build. So here's my 1s, and I'm going to put 2 electrons in. Here's my 2s, I'm going to put 2 electrons in. So that gives me 4. Now I need to put something in the next highest energy level, okay? Which is going to be the 2p. Okay, I can do that. So the interesting thing about the 2p is that p subshells have 3 possible orientations, right? So each p subshell has 3 possible orbitals. So here's one orbital, here's another orbital, and here's another orbital. Now, the convention is to write the label for this whole set of orbitals, this whole subshell, underneath the central one, okay? And I'm going to put 1 electron in. Okay? So that's boron. Well, what about nitrogen? Okay, well, nitrogen has 7 electrons. So I'm going to do my 1s, I'm going to do my 2s, here's my 2p. Okay, so I do my 4 here. And then, now what do I do? Okay, I could do 1, 2, 3. Okay, or I could do 1, 2, 3. Okay, and both of those would be ways of representing 2 electrons. I'm going to kind of write them all out here. Okay, so the third rule is Hund's rule. Orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron. Okay, so within a subshell, all the orbitals have the same energy. Okay, we can kind of see that when we look at something like this, right? Each of these 2p orbitals has the same energy. Each of these 3d orbitals has the same energy. Okay, so instead of putting 2 electrons in the same orbital, you put 1 electron in each of the orbitals, and then you go back and fill in. Okay, so this is correct. This violates Hund's rule. Okay? All right, so that's orbital notation. And I'll have you do some samples of that, and then we'll talk about electron configurations.